As with the last chapter, we started with categorical data, which is proportions. So categorical data, remember, is anything that you can't really do math with your data, you can only categorize it. And whenever we have categorical data, the only real statistic that we can talk about is proportion. Okay, then we moved on to onto means, and that's what we're going to talk about today. We're going to talk about how to carry out a significance test for mu, which, remember, is the population mean. Okay, there are, again, 3 conditions for conducting a significance test for a population mean, and they are the same 3 that we had for confidence intervals. And the same 3 conditions, though we did them a little differently for means than we do for proportions, but they're the same 3 nonetheless. Random, normal, independent. Okay, so with random, it either has to be a random sample, so your sampling method has to be random, or if it's an experiment, and let's not just let experiments, fall to the wayside, they're important too. If it's an experiment, it has to be random assignment, meaning that my subjects may be volunteers, but I randomly assign them to their treatments. Okay, with independent, remember, if you are sampling, it needs to be the 10% condition. And if you're not sampling, if you're flipping a coin or shooting free throws, something like that, you need to mention how they are independent of one another. However, most of the time it's going to be the 10% condition. Okay, normal is the one that differs. This is the one that's different from when we're talking about proportions. Normal is central limit theorem if your sample size is greater than 30 or greater than or equal to 30. Normal population, and if your population is normal, it does not matter what the sample size is. And if your sample size is less than 30, so this doesn't apply, and your population is not normal, that is when you need to graph your data for anything less than a sample size of 30. Okay, and remember, if your sample size is 15 or over, like 15 to 30, it can be a little bit skewed as long as there are no outliers. But if your sample size is less than 15, then it needs to be relatively symmetric with no outliers. Outliers are never okay. So if it's 15 to 30, it can be kind of skewed as long as there's no outliers. Less than 15, it needs to be roughly symmetric. So let's look at this example. A classic rock radio station claims to play an average of 50 minutes of music every hour. However, it seems that every time you turn to the station, there's a commercial playing. To investigate their claim, you randomly select 12 different hours during the next week and record what the radio station plays in each of the 12 hours. So here are the number of minutes of music in each of these hours. We're going to check the conditions for carrying out a significance test of the company's claim that it plays an average of 50 minutes of music per hour. Okay, so we're going to just check the conditions. We're not going to do the actual significance test yet. First condition is random. And it says right here that we randomly selected 12 hours. Okay, the next one is normal. And because I can see that there are less than 30 stations, and it doesn't tell me anywhere that the distribution of the minutes of music they play per hour is normal, I need to graph these. So, again, nothing fancy. The smallest one is 44, and the largest one is 51. So 44, 46, 48, 50, 52. Well, actually, 44, 45, 46, 47, 48, 49, 50, 51. So let's just make that easy. 44, and then I'll label it. Okay, so 44. 49, 45, 51, 49, 53, 52, 53, 49, 44, 47, 50, 46, and 48. Okay, so we can see our dot plot here of our 12 radio stations. It seems to be, relatively symmetric. Okay, I go low, I go high, I go low again. No outliers, so that's what we're going to say. Sample data is roughly symmetric with no outliers. And we have independent, and I'm going to put that one up here. Okay, because we are sampling here, this would be the 10% condition. So we can assume the station plays more than, and 10 times 12 is 120. So we can assume the station plays more than 120 hours of music in a week, because he sampled these all the same week. So there are our 3 conditions, all checked. Notice I described how I checked each one of them and how each one of them are met. And they all work out beautifully. So we could do a significance test for this. And we also, these conditions tell us that we could also do a confidence interval for this if we so chose. Okay, so let's talk about the test statistic. Remember, with proportions, just like with the confidence interval, we use Z. We use the Z-score, we use table A, okay, etc. With means, okay, it depends. If we know the population standard deviation, okay, and that's the population standard deviation, not the sample one, it's not the standard deviation of the sample means, like from the sampling distribution. This is the population one here. Then we can also use Z in table A. However, most of the time when you're dealing with means, you don't know that because all you have is your sample data. So most of the time, we are not going to know the population standard deviation. Instead, all we're going to have is S of X, which means that we are going to use the T distribution because it's more robust than Z. And remember, the T one is shorter and fatter than the Z one is. The Z one, this is standard normal, which is the distribution for Z. And this one here, the shorter one that's got the fatter ends, okay, that's T. Okay, so how do we calculate p-values using the T distribution? You are going to calculate it the same way. That's why on the formula sheet it just says test statistic instead of T. You are still going to use your sample mean minus what you assume the population mean to be divided by the standard deviation of the sample means, okay, which is, remember, if you have the sample standard deviation instead of the population one, it's the sample standard deviation over the square root of n. Okay, then you're going to use table B. And we're going to talk about how to do both of those things. Okay, so let's look at a couple examples. One says find the p-value for the less music example. All right, so I go back to my less music example. And in order to find the t-value, there are a couple things I need to know. I need to know x bar, I need to know n, and I need to know my standard deviation, my sample standard deviation. The easiest way to find these is to go to the calculator. So pull up a calculator. I'm pulling up Inspire. That's what I have on my computer, but yours will work either way, Inspire or not. And then I'm going to enter in my 12 pieces of data. So to do that, I'm going to add a list and spreadsheet page. Let's name it minutes because these are all minutes. Oh, it can't accept that because Min is a shortcut for minimum. So 44, 49, 45, 51, 49, 53, 49, 44, 47, 50, 46, and 48. And that's 12 pieces of data. And then I can come over here somewhere into the white area, or I can add a new page. And let's just go ahead and add a new page. So Control Doc. And I'm just going to add a calculator page. Menu, statistics, stat calculations, one variable statistics. Okay, I only have one list, and my list was minutes. Okay, that was the name of my variable. All of the rest of this will stay blank, and there it runs all of my stats for me. And remember that what I want to see from, or what I need here, my X bar, is this right here, this 47.9167. Okay, so 47.91 or 92. I know that N is 12. And then I need my standard deviation of my sample here. And remember that you always want the S of X, which is 2.81. Okay, so there we go. And then in order to calculate my test statistic, okay, I need to take that and say X bar, which was the 47.91, minus the population mean, which in this case we're assuming is the 50 minutes, okay, of music they claim to have, divided by my standard deviation, which was 2.81, okay, which I have to divide by the square root of my sample size, which was 12, okay, because that gives me my standard deviation of my sample mean, so of my sampling distribution. So I do this math here, and I'm already on a calculator part, so I can go ahead and say that. I want to need a parentheses. 47.91 minus 50 divided by, and then another set of parentheses to do the standard deviation, which was 2.81, divided by the square root of the sample size, which was 12. And we get negative 2.5765. So you could say negative 2.57 or negative 2.58 would be the t-score. So negative 2.5765, so you could say negative 2.57 or negative 2.58 would be the test statistic. Or you could call it the t-score. Not the z-score, but the t-score. Look at something. Our problem here is asking us, basically, what is the probability, because we don't think that they are playing 50 minutes of music per hour. So basically we're looking at what's the probability that I would get an X bar, a sample mean, that is less than or equal to the 47.91 if they really are playing the 50 minutes. Okay, which also means that I'm asking, okay, basically what's the probability that I'm going to get a t-score that's less than or equal to negative 2.57. Okay, the thing I know about t-distributions and the standard normal distribution is that if I'm looking for something on this end that's less than negative 2.57, that's the same thing as having something on this end that's greater than positive 2.57. So this is the same as asking this. That's an important distinction because the t-distribution table, table B, only tells us greater than or equal to. Okay, so remember that as we look at this table. It only tells us greater than or equal to. So here's what the table looks like. We've used it before to calculate the t-statistic for our confidence intervals, but this time we're going to use it a little bit differently. Then I was looking for the t-statistic, and now I have it. So see how I said it only does greater than? Remember that ours was 2.57. Okay, and so what I'm going to do is I'm going to look through here for 2.57. Something as close to it as possible. And I see here's 2.5, here's 2.567, okay, and 2.583, but there's something else that I have to look at, and the other thing that I have to take into account is the degrees of freedom. Remember, degrees of freedom is n minus 1. And so, since our sample size was 12, our degrees of freedom is 11. So it's got to be on this row, and the closest thing on this row to 2.57 would probably be this 2.718. Okay? It's between this and this. Which means if I scroll up, my p-value is going to be somewhere between 0.02 and 0.01. Okay, that's how Table B works. The thing about Table B is it won't tell me my exact p-value. Okay, it won't tell me my exact p-value. It just tells me two values that it's between. I know that my p-value is greater than or equal to 0.01, but it's less than or equal to 0.02. Okay, well, if my alpha value is 0.05, then this is enough to reject the null, because I know that either one of these, whatever it's between, is actually still less than the alpha. So you don't actually have to know the exact p-value in order to reject or fail to reject the null. You just have to kind of have the area and know that it's less than your alpha. So that's the thing about the Table B. Okay, you can, though, also do this on the calculator. Just like there is a normal CDF for working with the standard normal curve, our z-scores, there is a t-CDF when you go to Menu, Statistics, Distributions. There's a t-CDF for working with the t-score. Okay, so it works the same way. I put my lower bound in as negative infinity. I put my upper bound in as my t-score, negative 2.57. And then I put my degrees of freedom in as 11. Because my sample size was 12, I hit OK, and it gives me the 0.013, which I see is between 0.01 and 0.02. Okay, so that tells me right there. This goes along with what Table B said. So if I wanted a more accurate table, or a more accurate p-value, then the calculator is a way to do it. But either one or the other should be fine. So let's look at this next one. It says to find the p-value for a test of the null hypothesis mu equals 10 versus the alternative where mu is greater than 10 that uses a sample of size 75 and has a test statistic of 2.33. Okay, so I've already calculated my t in this case, and if my sample size is 75, that means my degrees of freedom is 74. Okay, so if I go to Table B, my biggest problem with Table B lies in this degrees of freedom. Because remember, if I can't be exact with my degrees of freedom, I need to be more conservative, which means I need to go down. So I need to pick 60 instead of 80. Okay, so I go to 60 and I scroll over to where I see the 2.33, and the closest I can get is between these two, 2.099 to 2.390. And when I look up, I see the same thing. My probability is between 0.02 and 0.01. Okay, So I know my p-value. I know my p-value is greater than or equal to 0.01, less than or equal to 0.02. And I actually, because it wasn't any of these, actually know that that's not even greater than or equal to. It's just greater than and less than. Okay, so let's say I needed to be more specific. And in this case, using the calculator is going to get me much, much more specific. And it might even give me a lower p-value than this because I can actually use my degrees of freedom. Remember, this was used as a degrees of freedom that's 60, which is going to be more conservative, and remember, we're going to have more information in the tails than one with a larger degrees of freedom. So I'll go to my calculator, menu, statistics, distributions, TCDF. Okay, this time it was greater than, so I'm going upwards. So my lower bound is my t-score of 2.33. My upper bound is some really large number, or I can use the keyboard over here to do infinity. And my degrees of freedom is 74, since my sample size was 75. I hit OK, and I get 0.011. So really, really close to this bottom one over here of 0.01. Okay, so using the calculator, I get a p-value 0.011. Okay, so let's look at the last example. Find the p-value for a test of the null hypothesis mu equals 10 and the alternative hypothesis mu is not equal to 10 that uses a sample size of 10 and has a test statistic of negative 0.51. Okay, so let's remember with the two-sided that it is a little different from the one-sided. Remember that with a two-sided, I take what I find on one end and I have to multiply that one by 2 so that it takes into account everything here. Same thing here. Whatever p-value I'm going to have to find, it's got to be multiplied by 2. Okay, so I know here that thanks to this, my degrees of freedom is 9, which means my table will help, because that's a small enough one that it should be pretty accurate. So here's my t-value. Let's go look at our table. I go to my degrees of freedom is 9, and I go look for negative 0.51, which would be positive 0.51. And notice that it is less than any of these values, which means that my p-value is going to be greater than 0.25, because notice here, as these values go this way, they increase, which means that since it has to be to this side, it would be greater than 0.25. Okay, which means if I multiply that by 2, it would end up being greater than 0.5. So my p-value in this case, according to table A, is going to be greater than 2 times 0.25. So, which means that it's going to be greater than 0.5. Okay. Calculator, again, going to give me a more accurate response. So if I look at my calculator and I say menu, statistic, distributions, TCDF, in this case my lower bound can be negative infinity, my upper bound can be negative 0.51, and my degrees of freedom is 9. I end up with 0.311, which you see is greater than 0.311, which is not greater than 0.5, but I have to multiply by 2. So that would be 0.622. Okay, so let's check our understanding. make sure you pause the video for a second and try and answer the questions on page 570 yourself before coming back to check your answers. Okay, and you can also pause the video to look and see, to check out your answers because they'll flash on the screen pretty fast. Okay, let's do a whole example. Every road has one at some point, construction zones, that have much lower speed limits. So to see if drivers obey these lower speed limits, a police officer used a radar gun to measure the speed in miles per hour, or mph, of a random sample of 10 drivers in a 25 mile per hour construction zone, and there are the results. So can we conclude that the average speed of drivers in this construction zone is greater than the posted 25 mile per hour speed limit? Okay, so we have a sample here of data, and the question is, can we conclude that the average speed of drivers in this construction zone is greater than the posted 25 miles per hour speed limit? So, a couple different things that I can do. One of them is a significance test. So, we're going to state, and you're going to realize that these steps are pretty much the same, and the requirements are pretty much the same as with proportions. We want to test, okay, and we need our hypotheses. Let's let our null be, since we're looking at whether or not they're greater than the posted 25, then no difference would be if the real mean was 25. And the alternative would be if the real mean of drivers was greater than 25 miles per hour. Let's go ahead and put miles per hour at the alpha, and since they didn't give us a level, we're going to say 0.05, where mu is the average speed of all drivers in this construction zone. Okay, that's state. Then the next thing we need to do is plan. Okay, I need to name my test since I'm looking for means, which average tells me right there. Since I'm looking for mean, it's a one sample t-test for mu. Okay, and there are a couple different conditions, obviously, that I need to check. The first one is random, and it tells us that he took a random sample of 10 drivers. Then 2 is normal. Since it's only 10 drivers and it doesn't tell us that the population distribution is normal, we need to graph these. We can start, let's say, at 20 and go up by 2. So 20, 24, 26, 28, 30, 32, 34. Okay, 34 should be high enough. So this was 22, 24, 26, 28, 30, 32. Then we graph them. 27 would be here. 33 would be here. 32 would be here. 21 would be here. 30 would be here. 30 would be here, 29 would be here, 25 would be here, 27 would be here, and 34 would be here. So this looks relatively symmetric with no outliers. So, and let me label this. This is speed. No outliers. And then finally we need to do independence. And I am running out of room, so let's just do that one over here. Independence. We can assume there are more than 100 drivers in this construction zone. Okay, so again, all of my conditions check out. Random, normal, independent. Okay, so then it's the do step, and this is where I'm going to calculate the t-statistic. And to do that, I need to know x bar, I need to know n, I need to know my s of x, and I need to know my degrees of freedom. Okay, some of these I already know. I know he took 10 drivers, which means my degrees of freedom is 9. Let's get the calculator out. And we can just go back to this page right here, and we can name this MPH. And I know that we have already used this page once, but it won't matter to just add another one. And our values are 27, 33, 32, 21, 30, 30, 29, 25, 27, and 34. 10. Perfect. And I need my one variable statistics. So I'm going to hit menu, statistics, not that, menu, statistics, stat calculations, one variable statistics. Oops. Okay, I only have one list I'm working with. I want to work with MPH. All the rest of these can stay okay. And there we go. And I get what I need. I need my average is 28.8 and my standard deviation is 3.94. Okay, 28.8 and 3.94. So then that means that T is equal to 28.8 minus the null value, which is 25, divided by my standard deviation divided by the square root of my sample size, because remember, I no longer am talking about just one value. I'm saying out of all possible samples of size 10, where does this one fall? So that's why I have to do this. And I plug that into the calculator, and I'm going to end up with 3.05. Okay, so then I can go to table B, or I can go to my calculator like we talked about earlier. But with a degrees of freedom of 9, 3.05 is going to be somewhere between 0.01 and 0.005. So, nope, 0.01 and 0.005. Okay, so I know that my p-value is going to be greater than 0.005, and it's going to be less than 0.01. Okay, so then conclude. Because, and no matter what p-value I have between these two, it's got to be less than the alpha value. So because the p-value, and remember our fill in the blank, is less than alpha, we reject the null hypothesis. There is convincing evidence that the average speed of drivers in this construction zone is greater than 25 miles per hour. There you go. Okay, full 4-step process. Alright, so let's look at this one. Given your conclusion in part A, which type of mistake, type 1 or type 2, could you have made? Because we rejected, that means that the only type of error we could have made is the type 1. When we rejected, when we should have failed to reject. Okay, that's a type 1 error. So what does this mistake mean in context? It is possible that the drivers do not really average greater than 25, and we just think that that is the case. Okay, that's what this means. This is when I rejected when I should have failed to reject, so that means I think that the average speed of drivers in this construction zone is greater than 25. In reality, it might not be. Okay, so let's look at one more thing. Let's look at two-sided tests. Okay, in the children's game Don't Break the Ice, small plastic ice cubes are squeezed into a square frame, and each child takes out turn tapping out a cube of ice with a plastic hammer, hoping that the remaining cubes don't collapse. So for the game to work correctly, the cubes must be big enough so that they hold each other in place in the plastic frame, but not so big that they are too difficult to tap out. There's a machine that produces the plastic cubes, and it is designed to make cubes that are 29.5 millimeters wide, but the actual width is going to vary a little. To ensure that the machine is working well, a supervisor inspects a random sample of 50 cubes every hour and measures their width. Okay, so here we have the output from 1 hour. Part A says to interpret the standard deviation and standard error provided by the computer output. Okay, the standard deviation tells us this. The widths of the cubes are about, and I look up here and I can see what my standard deviation is. It's the third one down. 0.087 millimeters from the mean width. Okay, that's what standard deviation means, that each individual width on average, okay, is about that far from the actual width. Okay, the actual mean width. Standard error means that in random samples of size 50, the sample mean will be about 0.013 millimeters from the true mean on average. Okay, those are the difference. In theory, they have the same kind of meaning, but for different scenarios. Standard deviation talks about 1 cube. So the width of any cube on average is about 0.087 millimeters from the mean width. Standard error talks about in samples. So in random samples of size 50, any mean, okay, will be about 0.013 from the true mean on average. So whatever the actual mean of the population is, so like this is probably somewhere in the vicinity of 0.013 millimeters away from the true mean. Okay, do these data give convincing evidence that the mean width of cubes produced this hour is not 29.5 millimeters? Okay, so this tells us to use the significance test. So we need to do our state. And let's do this on another sheet so that we don't run out of room. We need to do our state. The state we want to test, okay, the null is going to be that mu is equal to 29.5, because then that would be a statement of no difference. Ours, the mean that we got, is equal to the true mean. Okay? Otherwise, it's not equal to 29.5. Okay? Where mu equal the true mean width of cubes produced this hour. So out of all the cubes produced in an hour instead of just our sample. Okay, and we also want to make sure that we say that alpha, even though they gave it to us, is 0.05. Okay, then I want to plan. We are going to use a 1 sample t-test for population mean, which is mu. If you don't have mu, you can write out population mean. So like if you were doing this for a paper and wanted to type it out, we need to check our conditions. Random. the inspector takes a random sample of cubes. Normal. The sample size, which is 50, is large enough for the central limit theorem to apply. So we can consider it okay to use T procedures. And 3, independent. We can assume that more than 500 cubes are produced in an hour. There are our conditions. Okay, now it's time for the do. Okay, the do is our actual value, which is really close to the 29.5. Okay, because I got to make my T statistic. It was 29.4943 minus 29.5 divided by 0.0877 divided by the square root of 50. Okay, so I go to the calculator and I'm going to type this one in. Parentheses, 29.4943 minus 29.5 divided by parentheses 0.0877121 divided by the square root of 50. And I get negative 0.4595. Okay, so I also want to write that down. Negative 0.46. Okay, I want to make sure I write down that my degrees of freedom is 49 since my sample size is 50. Even probably want to write down, even though they gave it to me, that X bar is 29.4943, just so that everyone knows that I know what I'm talking about. 0.0877. Okay, then I go to my table, and 49, I'd have to go back to 40. So I could do this and go over, or I could go to my calculator. With the T values, I really like the calculator just because you know that you're getting a good result. So menu, statistics, distribution, TCDF, I'm looking for not equal to, but so I can go less, since it's a negative I need to go less than, so that would be negative infinity or some really big number. This would be negative 0.46. My degrees of freedom is 49. And I hit OK. And I get 0.323. So my p-value, and because it is two-tailed, I need to multiply that by 2. And I end up with about 0.646. Then I conclude. Okay, in the same way that we always do. Since the p-value is greater than alpha, we fail to reject the null. There is not convincing evidence to say that the width of the plastic cubes produced this hour is different from the standard 29.5 millimeters. So, notice exactly the same with it being a two-sided one, except I have to multiply my p-value by 2. That's the only difference you ever make with one-sided versus two-sided. In two-sided, I have to multiply my p-value times 2. Okay, so let's go back here and look at this. Let's calculate a 95% confidence interval. Okay, and see if our interval supports our decision. Okay, I'm not going to go through the state plan and all of that. We're just going to do the interval. Okay, the conditions are the same. You know how to state it from the last chapter. We're just going to do the interval. Okay, so remember that the interval in this case is our point estimate, which is always x bar when you're looking for means, plus or minus this t star value that's decided by this confidence interval, and the fact that our degrees of freedom is 49, times the sample standard deviation divided by the square root of n. Okay, I know all this information. I know that my sample mean was 29.4943 plus or minus whatever I am getting here. And I know that my standard deviation, which would be my standard deviation of my sample would be 0.0877 divided by the square root of 50. And now all we're missing is our critical value. Notice this is the standard deviation of my sample. This is my sample size. Okay, square root of my sample size. So now this is how I get my t-star value. If I'm using my table, which is what we're going to use today, I go find degrees of freedom, and I have to use 40. And then I scroll over until I get to my 95%. Okay, 40, I get to my 95%, 2.021. Okay, now remember, this one's going to be very conservative because I know my degrees of freedom are 49, not 40. But I can do this and it'll give me a wider interval, so I'm more sure to get the right answer. Like I'm going to go the wider versus smaller. Okay, so 2.021. So what goes here? Remember, this came from table B. And I'm going to actually type all this into a calculator and do the math. 29.4943 plus, okay, my 2.021 times my 0.0877 divided by the square root of 50, which was my sample size. And I hit enter. There's 29.52. And then I go here and I say subtract. So I delete this and put subtract. And I get 29.47. So this interval down here goes from 29.47 to 29.52. Okay, notice that 29.5 is right there in the middle of this interval. When it is in the middle of my interval, that would be the equivalent of failing to reject. Because yes, it's one of the values that's in this interval, so that is totally and completely and possibly what the true mean is. However, the true mean also could be 29.51 or 29.49 or 29.48 or 29.475. It could be any value between this and this. Okay? So when I am looking to fail to reject, that's what I'm looking for, that the value is in here somewhere. Okay? That's how, remember how confidence intervals and two-sided tests are related. If I am rejecting, the value has to be outside of my interval. And if I am failing to reject, the value is inside the interval. And in this case, since the value is inside the interval, it goes along with the fact that I needed to fail to reject. Okay, don't think that you could just use any confidence level and any alpha level. Remember that whatever your alpha level is plus your C needs to equal 1. Okay, so in this case, alpha was 0.05, C is 0.95. They have to all equal 1, but this is how they go together. Fail to reject, value should be inside your interval. Reject, it should be outside your interval.